okay, it's obnoxious. I'm trying not to be loud.
Like a mouse.
I know, they make all kinds of sounds.
Should not put by the camera though, because that's going to be obnoxious.
Next, Steve, on today.
Yeah, he's sick.
Okay, page 34 is where you need to be at. Okay, last week we started going over this. Okay, we're going to go over it again. We're going to talk about two-column proofs and proofs with truth tables. Some things you need to highlight here are these three rules. Okay, so when we're looking at conjunctions, so we got premises and conclusions. When we have more than two premises, okay, we start working with this idea of these three rules to prove that different arguments are valid. So when we're showing that an argument is valid, one thing some rules we can follow here, okay? We need to show a proof in several steps, so we're going to do today with two-column proofs. Okay, we have to give a reason for each step we show. We're going to see that. We have theorems of logic that we went over on page 20 and page 28. Okay, write those pages down at the top of this page. Page 20 and page 28. Page 20 and page 28. You need to be able to refer back to page 20 and page 28 frequently to be able to do well on this particular section that we're going to cover today. So make sure you write those pages down. They're key in doing well. These are some rules we need to think about. The conjunction of two premises follows from the premises. Meaning, if I have two premises, I can make a conjunction with those. Okay, if I have at least two, I can make a conjunction with them. If I'm given two premises or three, you can combine those premises using conjunctions in different ways. And that's what we're going to look at today. The conjunction of a premises and the conclusion of a valid argument follows. Okay? If we take the conjunction of a premises and the conclusion of a valid argument, we're going to see how those combine today to give us proof that our argument is valid. The conjunction of two conclusions of a valid argument follows from the premises. Okay, another rule. Again, we're going to see how this works today when we're looking at our two-column proof. So here's the thing. On the note here, when checking the validity of an argument, carefully list each step and give the reason that step can be taken. If an argument cannot be proven, so these rules are ways that are reasons that we can combine some arguments, or some steps, sorry. So some of the steps we make, these are some reasons that we'll be able to make those steps and to show that our argument's valid. So we're showing that our conditional statement is a tautology in the end, right? We've talked about this all week last week. We made truth tables where we said, look, we want a conditional statement. That conditional statement's a tautology, then our argument's valid, right? That's going to come back again today too. So there's going to be some stuff that's new today and some stuff that's not so new. We talked about briefly last week, if we can show one case where the hypothesis does not give us the conclusion, in other words, we show that if hypothesis, then the conclusion has a true value of false. So if our conditional statement is false at any time, we can show that our argument's not going to be not going to be valid because our conditional statement's not going to be a tautology. Okay, we started with this last week too a little bit. We looked at this argument. We're going to break it down better today. Okay, last week I didn't explain it the way it needed to be done. I think I got a better handle on it today to help you guys understand what's happening So our argument is right here. Okay, these two lines. If it is raining, the picnic is canceled. If it is not raining, the soccer game is not delayed. But the picnic is not canceled, therefore the soccer game is not delayed. So R is it is raining, P is the picnic is canceled, S is the soccer game is delayed. The symbolic form of our argument. Here we got premise 1, premise 2, yes.
I'm confused about that because the soccer game could be delayed for a different reason besides it if it's raining.
We're looking at just this argument. You have to forget everything else you think about soccer and rain and games being delayed. We're just looking at this specific argument to see if it's valid.
What if it's snowing?
Again, we're not worried about snow. We're not worried about any other weather. We're not worried about whether we like rain or dislike rain. We're not worried about whether we play soccer or don't play soccer. We're looking at the argument, okay? We have to really kind of forget a lot of other options we're thinking about. We're just saying this argument is valid. We're saying if it is raining, the picnic is canceled. Okay? Just stay with me for a second. If it is not raining, the soccer game is not delayed. But the picnic is not canceled, therefore the soccer game is not delayed. So these are our statements. We don't care if they're true or false right now. We don't care if we agree with the argument. Okay? It doesn't matter if you agree. We're looking at whether it's valid. Okay, we're looking at validity here. So, in symbolic form, if we were to take this argument, write it as symbols, we have if R then P, a conditional statement of R and P. Then we have a conditional statement of not R and not S. Okay, so if R then P is right here. So that's this part right here, this first sentence. And then if not R, okay, then not S, the soccer game is not delayed. Okay, these are our statements. This is our conditional statement. Okay, negation of R, or sorry, not R. If not R, then not S, and then not P is our last part here. But the picnic is not canceled. So our conclusion is therefore the soccer game is not delayed. That's not S. So we're looking at this whole argument to see if it's valid. Okay, we're used to saying, well, let's throw this in a truth table and look to see if it's conditional statements of tautology. We're not doing that right now. We're going to look at a two-column proof. Now, with a two-column proof, looking back at page 34, look at this statement right here. This rule. The conjunction of two premises follows from the premises. So we're going to take our two premises. How many premises do we have? 3, right? Okay, look at all 3 of these. Okay, we're going to try to so this is our proof. Whenever we have a two-column proof, we have statements on the left, reasons on the right. And our first statement was if R then P, and our second is if not R then not S, and then our third statement is not P. We're trying to conclude, okay, that not S is our conclusion. Okay, so we're saying if not, and then not S at the end. That's what we're trying to get to. Now, step 4 here, okay, premises, premises, premises. And these are given, given, given. So anytime you have your statements, okay, you always write down your givens first. In this case, our premises. Okay, write all 3 of them down. Oh, that's a premise and given, premise and given. Okay, that's what you do with the proof. You have to give your statements and your reasons. So this is what we start with. This is what we can work with. Now that we have these reasons, or these statements, okay, since this is what we can work with, we're trying to conclude not S. Okay, notice not S is our bottom down here. We're trying to show that these 3 statements get us to not S. So we have to make a map, basically, to show that not S is our conclusion. Well, our rule on page 34 says we combine 2 premises as a conjunction. If I take 1 and 3, these are 2 premises, right? We're going to put these together in a puzzle to help us get to not S. Okay, so this is going to help us get to not S. If we know that if R then P as a conjunction with not P, okay, the conjunction of premises 1 and 3, we can do that because of our rule. Okay, it's like the It's like an operation for us. We can do this right here. We're going to make a conjunction of two premises to help us get to not S. So we turn our premises into not S. So if I take these two premises and I make them a conjunction, okay, that if I take it and I make these guys a conjunction because of my rule on page 34. This conjunction can be described as not R by a rule of modus tollens. Okay, I want you guys to go look at page 28. Actually, don't go look at page 20. I'll pull up page 28. On page 28, this is what we got. Okay, don't go to page 28. Just stay here. Okay, I got page 28 right here. On page 28, rule of modus tollens. Okay, if I take a conditional statement as a conjunction with the not Q here, so if I have if P then Q and not Q, that implies not P. It implies not P. Okay, this rule, so if I can make this statement, I can say, well, that's a valid argument to say, well, not P. Right? This is a valid argument. This is not P. It implies not P. That's what we see on this right here with our proof. We see rule of modus tollens here. If we take a conditional statement with the conjunction of not P, that implies not R. Rule of modus tollens says we can do this. Now what we're going to do is we have a new statement to work with. I'm going to combine that with my premises up here, number 2. If I take this premises on number 2 and combine it with number 5 as a conjunction, I know I get if not R, then not S, and as a conjunction with not R, that's conjunction of premises 2 and 5. Okay, so I can take this result, combine it with 2, and say, look, this is what I get. This statement, by rule of modus ponens, okay, if I look at page 28 again, modus ponens says, look, if I have if P then Q as a conjunction with P, that implies Q. Well, it's not quite how ours looks. We have negations. It's the same thing, we're just got negations, that's fine. We have, the negations don't affect us here, the nots. Okay, using rule of modus ponens, we can say, well, if not R, then not S, as a conjunction with not R, that is not S. This is where we have to get to. So we used the above statements to get to this one. So if you can use what you're given to represent what you want, the conclusion, then your argument is valid. What you guys are going to have to do on your quiz on Friday. This is a lot, right?
Wait, on Friday?
On Thursday, sorry.
Oh.
Okay? Our Friday. In class anyway. What you guys have to do on Thursday is I'm going to give you the left side. You are going to have to look at the right side and give me the different state reasons and fill in the blanks. That is how your quiz will look on Thursday. Okay, this is going to be hard to do both. Yes? Okay. I think if you guys can follow this, you can read this and get something like this, to go to this, to go to this. I'm happy. We're accomplishing what we need to in this class for right now. So you guys will fill in reasons on Thursday. We're going to practice this today. Yes?
So, can you combine any two premises?
Yes, as a conjunction. So we combine those premises to get a certain conjunction so that we can use these rules, like modus tollens or modus ponens, or other theorems. So on pages 20 and 28, this is what you have. You have all of these rules, okay? All of these theorems. So these theorems help you get different conclusions. So you're going to use stuff on page 20. You're going to use stuff on page 28. And you're going to use the rules on page 34 to help you get the combinations. Okay? So what you're doing is you're combining different statements to get a valid argument, to prove a valid argument. So if you can make a valid argument with the pieces you have, it helps you show that your argument is valid in the end. Does that make sense? Yes. Yes. Okay, we're gonna look at another example. Let's look at the next one. Okay, this is where you guys need to start asking some questions. Okay? So this is difficult. This is probably the hardest part of prep is this week and a little bit of next week. Okay, for logic, it'll be the hardest week and a half. Then after that, when you guys come back, so not next week, but the week after, starting that week after, our second to last week, things start to get a little easier again. Okay, but this next week and a half is pretty difficult, so you need to be focused and ready to go. Yes?
Isn't this the fourth week?
This is week 4, yes?
And how many weeks are there? 6?
7. Okay, here's our new argument. We're going to check the validity of this argument. If an object is less dense than water, it will float. So we have statement I and statement N. The water displaced by an object will weigh more than the object. Or the object will not float. But the water displaced by the object does not weigh more than the object. Thus, the object is not less dense than water. Okay, so what we do is we identify the statements. Well, we have I, F, and N. Okay, statement I, F, and N. So I is object is less dense than water. F is it will float. So the water displaced by an object will weigh more than the object. That's statement N. Okay, or the object will not float. So will not float is what?
Not F.
Not F. Okay, let's write this down. Not F. Will not float. Okay? But the water displaced by the object does not weigh more than the object. What is this statement right here? The water displaced by the object will not weigh more than the object.
M? Not M?
Not N. Okay? Not N. Okay, I'm going to say water displaced does not weigh more. So we're identifying pieces here, okay? Thus, the object is not less dense than the water. What does the last state or last sentence represent? It's the conclusion, and it's not I, right? Okay, not I. Okay, I'm not gonna write that out. So not less dense, not less dense. So we can kind of identify where our statements are and what they are. Well, first we write our symbolic form. Okay, on your quiz, you will have to write the symbolic form by yourself. I will give you a P1, a P2, and a P3, and you'll fill this in.
What about the dotted line in the C?
Yeah, you have to do the C2. That's part of the symbolic form. All this is symbolic form.
I know,
So you have to take the statement. This is all here. You just have to fill in the blanks.
I know, but, oh.
Yeah, dotted line will be there. Fill in the blanks. P1, P2, P3, C means conclusion. So what you guys have to do is look at the statement, identify each statement symbolically. Well, we have a conditional statement to start. Then we have what kind of statement is this? A disjunction of M and not F. And then we have just not N for our last statement, our last premise. And then our conclusion is going to be not I. So we want to use these three statements to get not I. So we're going to combine them. It's like if you had 12 plus 17 plus 15. You're going to combine these to get a conclusion, right?
Yeah.
These are, in a sense, your premises, your statements. You combine these statements through addition to get a conclusion. We're going to use logic statements or logic theorems to combine our statements, though. There's no operation sign, right? We're going to use logic theorems, okay, and our logic rules to get the conclusion, to get the answer. Yes, Katerina?
Why is there, so like on the symbolic form, why is there less than on the statements? Like why is there more statements than what you given on the symbolic form of the argument?
So you mean these?
So no, why is there more statements than there is the things on this, on the table thing? Out of the 3 statements, why are there more statements?
Oh, these are the statements we're given. We're gonna make new statements to prove this, to show that this can be a conclusion. So we're saying, look, is this argument valid? We have to combine these statements to get the fact that this is a conclusion. So it's like, we're making statements within the statement to show that the statement is valid. We have to look at it a little more, okay? So you're looking down here, yes?
Yeah.
Okay. So, our statements, we had an argument on top. We want to know if the argument in the words is valid. We symbolically represent the argument. And we say, well, look, these are our statements from the symbolic representation. This is premise 1, premise 2, premise 3. We got to use the premises to get this. Usually to do this, we make a truth table. And we say, look, the conditional statement for the truth table is a tautology. And we're not doing that right now. We did that last week. We're going to jump back to it as well. But we want to know, is our argument on the top, does it make a valid conclusion? Well, using the premises, let's look at premises 2. We know commutatively the disjunction of M and not F can also be not F and M. These are equivalent, yes?
Yeah.
So we can make, by commutative property applied to step 2, we can make this new statement. So we haven't changed the statement. We're using the statement to make a new statement. Is that good? This is hopefully answering your question with this. We're still using the same statement, we just did a commutative property. Okay?
Well, why are you doing a commutative property?
Because we want to show that this gets us this.
I have a question.
Yes?
How are all of these statements proving that equals that?
We're showing that it's a valid argument. So
Yeah,
if we can
but-
turn those statements into the conclusion, it's like a transformer.
Yeah, but. like-
Okay? Think about, you guys have seen Transformers? You guys, oh man,
I've
this is,
seen
you guys
it.
really, okay.
I've seen
Let me think, what's another example?
I've seen Bumblebee.
We're trying to take the premises and say, hey, look, these premises put together make the conclusion. So you have to manipulate them. In mathematics, okay, go back to this idea. Let's do 2 times 4 plus x minus 3 equals something. In mathematics, we're going to manipulate this to look like something else, right? So this is an argument. I can manipulate it and say, well, that's going to be 8 plus 2x minus 3 equals something still. And that's going to be we're going to call it 5 plus 2x will be our argument. So what we can say is that this argument, when we make it look different by using our rules of mathematics, we can say that's 5 plus 2x. Is this a true argument? Is it valid?
Yeah.
In a sense, that's what we're doing here. It's not the exact same thing. You guys have to get rid of the idea it's going to be the exact same thing. We're using our logic rules. One of the first logic rules or properties we use here is commutativity. We're saying I can take M or not F and make it not F or M. Okay? We're taking all premises, we've got to use the premises to make this conclusion. Yes?
Can a conclusion be used in any of the statements?
Say it again?
Can a conclusion be used in any of the statements?
No, the conclusion has to be the end. The conclusion is the end. It's like what it's equal to. Yes?
How do you choose the like, how do you choose
Give me a second, I'll check.
Yeah, I was just gonna ask, do you do the property in like the same order every time, or are you gonna do like this?
Okay, that's going to go with her question.
So, on the ninth statement, it has to be divided from the statement.
Say it again.
On the statement number 9,
Hey, if she's talking, you might want to be listening, right? Okay, please listen.
so statement number 9 is the the conclusion? Why doesn't it say, any like conclusion instead of no?
We'll get there. Stay, don't jump too far ahead of me, guys. A lot of you guys have questions because you're looking at the whole thing. Okay? Don't let the whole thing intimidate you. Okay? Coming back to some of the questions. Is there a right way to do a two-column proof every time? Okay? No, there's not. I mean, there's some basic principles you have to follow. You have to give your premises first, or your given statements. Okay, you always start with your givens. Okay? It's like writing a paper. You're going to start with an introduction when you write a paper, right?
Yep.
Then you're going to give the body of the paper, and then you're going to give your conclusion, yes?
Yep.
So this is like our introduction. You guys can write that. That's like your introduction, the premises. The body of our mathematical paper here, our two-column proof, comes from using, okay, this comes back to your question, on page 20 and page 28. Those are the rules you're going to have to look at to get these reasons. So, who's done a Rubik's Cube before? Okay? Who's got the algorithm down to do a Rubik's Cube? How fast can you do it?
Around 30 seconds.
30 seconds, okay? If you don't know the algorithm, okay, we're used to algorithms as part of our problem. If you don't know the algorithm, it can take you quite a long time to do a Rubik's Cube, right? You have to try different things. You have to do trial and error, yes? If you've done a Rubik's Cube before, it takes you some time. But once you start to realize there's some patterns going on, in this case our pattern is going to be introduction, body, and conclusion. Yeah, that's our pattern. But the ins and outs of it, you have to try different things to get to your conclusion. It's like a giant puzzle. When you do a two-column proof, it's like a Rubik's Cube. You got to try different options. You got to put different pieces together. Jigsaw puzzles. I got jigsaw puzzle people here. Okay? My wife loves puzzles. There are 500, 1,000 pieces, whatever. Okay? Those are kind of our limits in our house. When you do a puzzle, you're going to do the puzzle probably a different way each time, but what's probably one of the best ways to start a puzzle? Yes?
With the, edges.
Get the edges and the corners, right? What's not your next step to kind of helping you in that puzzle? Work on the inside. Okay, you separate the colors. You put the colors in different groups and you start putting that inside together. This is a logic puzzle. So our insides, this is like putting our borders up and our corners and our edges. And this is taking that inside and we're saying, okay, what's going to work to get us to the conclusion? Well, the first thing that's going to help us is that we're going to take a commutative property from here to here. We're going to hold on to this for a second and just leave it here for a second here. Now we're going to say, well, if I know this is true, because I concluded that this can be this, now I can take my disjunction here and say, well, I can make this conditional statement because of this disjunction. This is why. If you look at page 20, we see right here. If I have a disjunction of, I'm going to go back to my proof. We have not F or M, okay? If we have a not, right here, denying the antecedent. Here we have a not P or Q, yes? You see that? That's logically equivalent to this conditional statement of if P then Q. That's exactly what we have on our proof over here. Our proof says, look, you have not F or M, that's logically equivalent to this statement. So we just manipulated step 2, this premise, to look like this, to look like this. That's part of the puzzle. Okay? Now, let me finish first. Okay? And I'll come back to you guys, okay? We go from here to here to here. Now we're using the conditional statement of if M, or if F then M, as a conjunction with step 3. because of our rule on page 34, we can make, this is our new premises. We've taken premises 2 and says, well, it's actually could be equivalent to this. That's good. And we take premises 2, our new premises 2, put it right here, and put it with premises 3. That's a conjunction of a valid argument 5 and premises 3. Okay, valid argument 5 and premises 3 can give us this conjunction. Let me finish first, okay? Once we get this, this is our rule of modus tollens again. If you have a conditional statement as a conjunction with not M here, so we have M here and not M here, rule of modus tollens says, look, that's not F. So we made another argument. Because rule of modus tollens is an argument. It's a valid argument. If you make this conjunction, that's not F. Which, in turn, we can now take premises 1, because we've used premises 2 and premises 3, right? You see that? We've used 2 and 3. We've got to use premises 1 to show us that the conclusion is going to be valid. Well, now I take premises 1 as a conjunction with my valid argument on 7. Okay? Valid argument 7 and premises 1. If I make those a conjunction, rule of modus tollens tells us, well, look, that's going to be not I. Which, that's our conclusion. That's what we got to. So we can take this guy right here, number 7, and combine it with our premises 1 as a conjunction. And we get not I. So we used all of our premises. We manipulated them. We took the pieces apart a little bit. We put them back together the way we want. And we get our conclusion. So if we get to our conclusion, it makes a valid argument. Because we used other rules to get to our argument. So we're using rules to prove a rule, essentially. Or rules to prove an argument. Okay, it's like when you guys ever seen a debate team? Yeah? Okay? When you're making a debate, you have to have statements and reasons throughout the whole debate. Otherwise, your argument's not valid. We took pieces, we took our statements, gave some reasons over here, and we took our statements and said, look, well, since we know this is equivalent to this, and this is a valid argument with this, we can now conclude here. So you're taking pieces that you know to get what you want. You're manipulating 3 statements to get to your conclusion. Yes?
When my first read, how do you choose the rules? How do you know what to choose?
Like a puzzle, you don't know what's going to work until you go try it, right? It's really, you have to kind of see it. You have to know your rules and say, well, I know I can manipulate it this way. There's no, it's not like this where you say, yep, I'm going to use distributed property and do that. It's not something you're used to, like something like this. You're used to this, yes? You guys got a problem? What's up? You got a problem? Okay. Okay, so we're going to take, this is normal for you guys. Here, we have a logical statement. These rules are, some of them are kind of the same as this, but we don't know these rules as well, so it's not as obvious. Answer your question. You just have pages 20 and 28. That's how you know. You're going to use those rules on pages 20 and 28, those theorems, to help you get what you want. If you can't get to what you want, you show one statement that it's not going to work, and it'll show you it's invalid. Yes?
Are we going to make a table like this?
Yes. Like I said, on the quiz, you guys will get this on the left, you fill in the right. So I'm going to show you this stuff. You just have to figure out which rule it's actually showing. Okay? You just have to be able to recognize it by reading. So if you guys can read this on the left and put it with this on the right, then you're going to be doing okay. Yes?
Is it a quiz or an exam?
Quiz.
So it's open book.
Yes. Yes.
This is the last quiz because you said
Yes.
only 3.
Yep, then you have an exam next week.
When are we done with the exam?
Okay, what we're going to do now, we're going to do exercise 15. Exercise 15. So go to exercise 15. What I want you guys to go ahead and do write this argument symbolically. Write this argument symbolically.
We have to do the proof.
I want you to write the argument symbolically right now. We're going to do the two-column proof, yes. So everyone, pencil should be going. You're writing an argument symbolically. You should have 3 premises and a conclusion. 3 premises and a conclusion. So you should get P1, P2, P3, conclusion. This is much how the quiz will be on Thursday. Read the argument, put it into symbolic form. Those of you that had questions earlier, did I answer them? Okay, raise your hand again if you step in. So, okay, what's my first premises? Yes, first premise. What? Very good. Okay, what's premise 2? Back. If E, then D. Okay, premise 3. Yes?
Not D?
Not D. Okay, let's look and see if these are right. The number can be odd, O, or it can be even. That's a disjunction, okay. If it is even, E, it can be divided evenly by 2. D, they tell you, hey, that one is D. So if E, then D. But the number cannot be divided evenly by 2. Sounds like not D. Therefore, the number is odd. What's the conclusion? Good. Okay, now we're going to list our statements and reasons. Okay, I'm going to write the first 3 statements. 1, O or E. 2, if E, then D. You guys give me the reasons. 3, not D. Get those 3 reasons down. Okay, get reason 4 down. So this is, this should be if E, then D. It's a D, D, and not D. Sorry, my D's are not very good today. Those are D's. Better D here. Okay, what's reason number 1? Raise your hand. Who's got reason number 1? Premise. Okay, reason number 2? That's a premise or a given, right? We can say premise or given. I don't care which word you use. Yes? Premise. Now here's the trick. Number 4. Yes?
Conclusion. Conjunction of 2 and 3.
Conjunction of 2 and 3. Very good. Conjunction of 2 and 3. Okay? Now, let's see if you guys can get this down. Because of this conjunction, what can I say for statement 5? say for statement 5? What can I say for statement 5, Maggie?
Correct me if I'm wrong, but I think it would be E, in parentheses, if E then D, conjunction not D implies O.
Implies, so you think an O goes here. So you're saying this implies O. Close. Close, not O. Not O, what do you think?
Not E.
Not E. Why? That's the reason. Why does this statement imply this one? Why?
Rule of modus tollens.
Rule of modus tollens. Good. Okay, so the not E is going to be useful. So that we've combined these two statements to get to this guy. Okay? We're going to use this in a minute.
I have a question.
Yes?
Who's modus tollens?
I don't know. Modus is going to be like not an operator, but I don't know where the name comes from. Now, what statement have we not used yet?
One.
We haven't used 1, right? How can we use statement 1 with statement 5? How can we use statement 1 with statement 5? What can we do with those? Yes?
We go, O or E as a conjunction of not.
Okay. What's going to be our reason for that? What do you got?
Conjunction of premise 1 and valid argument 5.
I can spell conjunction. P1 and argument 5, you said?
Valid argument 5.
Valid argument 5, very good. Even better. Questions on that so far? Okay, so we're going to make a conjunction there. Now, this one's not going to be as obvious. Okay, go to page. Well, actually, don't go to page 20. I'll show you page 20. Let's look, page 20. Maybe. Maybe not page 20. Ah, this page. Okay. Look at what I have here. Okay, look at F. I'm going to highlight it. Look right here. Look at where it's highlighted, right above the whiteboard. Okay, that's what we want. We're going to use distributive property to help us out now. So we've made O or E as a conjunction with not E. That helps some of you see it a little better. Okay, so I'm going to go back to our two-column proof. And this is what we have so far. We need a step 7. And I'm telling you the reason here is going to be that we're going to distribute this. So when we distribute over a conjunction, okay, if we go back here, we have a disjunction into a conjunction or a conjunction into a disjunction. Okay? So we've got to look at what we have here. We have a conjunction into a disjunction, right? So step 7, you guys can write yours below, okay? Step 7, our statement, is going to be O, or what?
Or E and not E.
Or not E. And,
You said not E in there.
it's not. So we're distributing the not E, right? Into the O. Yes? sorry, this needs to be, the and goes with this. Needs to be conjunction, this needs to be the disjunction. So disjunction with, now we got E and not E. Okay, so this is going to be by distributive property. So we used another rule to help us get this. Now why is this going to be useful? So that's what we got to look at next. We got to take this disjunction here and figure out what can we do with it. Well, E and not E, what's that?
False.
What's another name?
Conjunction.
Not a conjunction. We look at, again,
Logically equivalent? Not
oh, you're so close.
Not logically equivalent?
Wait, what did you label number
We have
seven?
E and not E. We can rewrite this as a
Conjunction.
Converse. Contrapositive.
so we have tautologies and what? Contradictions. So if I have E and not E, that is a contradiction. Okay, then if I have a conjunction as a, so conjunction of O and not E as a disjunction with a contradiction. Okay, let's write the reason down here. So it's going to be inverse elements. Inverse elements. This is on page 28. You get this rule, inverse elements. This rule is on page 28. Step 9.
What did you label number 7?
Huh?
What did you label number 7?
Distributive property.
Or then, or
What is
C?
the,
Then, or C.
Or C, yes.
does that mean or complete?
So we're saying this statement right here is a contradiction. So we turn this into this. Okay? E and not E is a contradiction. We can rewrite it like this.
How do we know?
Once we get a contradiction here, okay? Yeah.
Why? So, why are we using so many more C's than
Because we have to get to the
the other
conclusion.
one?
We have to get to the conclusion. It takes more steps than. Guys, proofs are not the same. It depends what you're given, the steps you take. The steps here, we were given different things here, so to get to our conclusion, it takes a lot more steps. Does that make sense? Answer your question? So now, on step 9, if we know that this is an inverse element, okay, identity property of contradiction says, well, hey, look, this statement is equivalent to O or just not E. Okay? So this statement,
Or and?
not E, sorry, and not E. Okay, that's going to be by rule of identity property of contradiction. So identity, again, this is on page 28. Identity property of contradiction. Hey, this is exercise 15. Make sure you have this written down, otherwise you're probably going to miss it. Like, you should have a 2-column proof on this. There's a line there. So it's just continuation, statements, and reasons. Make sure you have it written down. Okay, we have one more. Okay, if I have... Oh, I wrote that wrong. That's okay. And then this O or not E is equivalent to something else. What's it equivalent to and why?
Equivalent to regular E. Yeah, it's equivalent to regular E. Equivalent to O.
Okay, look at page 28 at the bottom. No, page 33. Sorry, page 33 at the bottom. No, 28 at the bottom. My bad. I got it right now. Right page, 28. Sorry. 28 at the bottom, theorem 8. I have O or not E. Or O and not E, sorry. O and not E. That implies what?
Implies P. Implies O.
By theorem, this is on page 28. Theorem 8 tells us this. O and not E is O. Yes?
I have an implication for you. I'm buying a steak for lunch because it's 12:20.
We might be able to do that.
It is 12:20.
Okay, I'm gonna answer another question real quick. I will give your tests, your exams, okay, to Robin, Brooke, right?